Okay, let's get started. So welcome everyone to another lecture in our ID 5130 parallel scientific computing course. So today we will kind of try to wrap up the OpenMP programming part. Okay. So in the last lecture we were looking at essentially some miscellaneous directives as well as the some synchronization directives, right? As part of the synchronization directives, we looked at directives such as single, right? Master. We looked at what is critical, right? We also looked at something that is called barrier, as well as we looked at what is atomic, right? And we also discussed how the atomic directive is different from the critical directive, right? So we looked at all of these. There is essentially one more directive that is basically for the data synchronization. So we are going to look at that, and then after that we are going to look at briefly at one work sharing construct that we did not study till now. So we will look at that, and after that we are going to look at in today's lecture the some of the runtime functions, okay, that are provided by OpenMP library. Okay, so we're going to see all of these in today's lecture, and then that should pretty much wrap up all the OpenMP related function calls and the directives. Okay, so the one of the data synchronization directives that we would like to study is known as the flush directive. Okay, so what the flush directive does is this basically flush directive should be kind of used at a kind of a point, a sequence point in the code where each of the threads, where all the threads should get a consistent view of the variables, okay, or all the threads need a consistent view of the variables. I mean, we by variables we mean, of course, we mean the shared variables. We have the variables, okay, so that each thread has access to the correct value stored in the variable. Okay. Now this may seem like, okay, why do we need such a thing? But rather it is sometimes required, not all the time. For example, let's say I would kind of take a couple of examples. So the first example I would like to give is, for example, let's say you have written some code, okay, and then OpenMP without your notice decides that OpenMP decides that that code is not really optimum. As a result, it may try to change, within the scope that is provided, it may try to change some of the lines or the way it is implemented, so that it will be little more optimized version of it, okay, or a better version of it. Now when it does this thing, and if you try to access some of the variables before the accessing variables before the directives end, okay, may provide some kind of may provide incorrect values, okay. So in such instances, to essentially make sure that all the variables that we are using have kind of a data synchronization, we can use the OMP flush directive. Okay, so that is basically one example. The other example is, let us say you have an array of elements. Okay, so basically we have an array of elements, and then essentially this array contains okay, I'll just draw it with, okay, so you have an array of elements, and then basically you know, a part of this array is basically executed by different threads. Okay, so basically you have one thread executing this, and then we have another thread. This is basically shared between the threads. Okay, or you know, or rather we can say it's kind of yeah, it's kind of shared by the threads, but then the threads do not access the other range. Okay, so when you do something like this, so then what happens is that it is possible, based on the way the OpenMP kind of OpenMP kind of implements, that some of the variables that are being updated by, you know, some thread T2 may not be really visible to T0 as such. Okay, so in such cases we may need to kind of provide a data synchronization, and that is what will be provided by this particular function. Okay, so what you do is you basically make a call to OMP flush at certain locations where you need data synchronization. So you can say hash pragma OMP flush in C, or you can say exclamation dollar OMP flush. Okay, now this seems to be fine, but then there is a problem with this, because if you just leave OMP flush, then this entire operation can be costly. I mean costly because what happens is that if you just leave it open like this, if you say OMP flush, then OpenMP will kind of try to you know, update or sync all the, you know, shared variables in the scope. So this could be sometimes a costly operation. As a result, it is a good idea to specify only those variables that you feel like would require an update or a synchronization to be specified in the flush operation. Okay, so basically that is specify only those variables that would need a synchronization. Okay, we'll specify only those. That means, how do you specify that? Basically include them in the list after the pragma statement, after the flush statement. Okay, hash pragma OMP, you have flush, and then you essentially include the list of variables separated by a comma. Okay, so exclamation dollar OMP, you say flush, we have variable 1, variable 2, all the way to some variable n. Okay, so that is how you can kind of make sure that the flush operation would not become very costly. Rather, it will only update or synchronize, you know, required variables. Okay, so that is what you should do. Fine. So that is kind of you know, the remaining synchronization directive that we kind of could not finish in the last lecture. Okay, now I'll get back to the some of the you know, discussion on the work sharing constructs, where we did not study one of them. So we have so the next what we're going to look at is we are going to look at work sharing constructs. Okay, so can you recall what are the work sharing constructs in OpenMP that we have studied? We have only studied one of them, right? Work sharing construct is basically, or work sharing directive, the only one we have studied is basically the for loop or the do loop, right? Work sharing construct, that's what we have studied. Now what did we say? We said if you have a hash pragma OMP parallel, or if you have hash pragma or if you have exclamation dollar OMP parallel do, then the following for loop or do loop will be parallelized by the OpenMP during the runtime, right? So that's what we have done, and that is where the sharing of the work in terms of the loop index variable will be carried away and it will be split between the threads. Okay, so they are going to split this entire you know, n iterations between themselves depending on whatever you specify or based on the default values. Now that is one work sharing construct that we have learned, and we have learned to kind of or identify to be written like this, right? We have written hash pragma OMP parallel for, and then we said it has to be always followed by a for loop, right? That's what we have written in C. And then in Fortran we have written exclamation dollar OMP, I'll just write in lowercase, parallel do followed by a do loop, do I equals 1 to some n, and then you have a piece of code, you have end do, and then you have the closing directive exclamation dollar OMP and parallel do, right? So this is basically end parallel to, right? Okay, or end parallel. So fine. So that is what we have written. Now there is one more work sharing construct that we would like to study, but then before that I would like to kind of draw your attention to this construct whatever we have studied already. Okay, so we said basically hash pragma OMP parallel, right? And also we said exclamation dollar OMP parallel do or parallel for and parallel do, right? These two, these are actually to be clear, these are actually combined these are combined parallel work share constructs. We have not kind of looked at it from that perspective till now. What do we mean by combined parallel work share constructs is that they basically offer a shortcut to write a parallel block together with a for loop. Okay, shortcut to write a parallel block plus a for loop, okay, or a do loop. So that means so we have kind of combined those two. Otherwise this can be basically written as separately, right? How do you write it separately or differently is basically you have a hash pragma OMP parallel, right? And then here you can specify all the list of the shared variables or private variables and all the clauses. Then you have some statements. Then you can actually have a hash pragma OMP for, right? And this is where you would have your for loop, right? Essentially you have a branching here and then you have another branching here, and this for loop closes here and the outer hash pragma also closes here. Okay, so so you can have something like this. This is basically what it does is you have forking happening here, right, by the master thread, and you enter basically a parallel region. So this is the parallel region or the block, and inside that, so this is your already the parallel construct, and then you have a work share construct here, right? So this is your hash pragma OMP for. Okay, so the same thing can be done for Fortran as well. So basically you can write exclamation dollar OMP parallel, right? And then you can specify a list of the shared variables or private variables or any other clauses that you want to specify, and then you can also specify exclamation dollar OMP do, right? Exclamation dollar OMP and do, and after this do you would need to have a do loop 1 to something and then end do, and then of course you would have eventually exclamation dollar OMP and parallel. Okay, so that means we have again the parallel construct here, and then we have the work share construct here. Okay, so till now we have kind of combined these two into one, right? We have used this combined statement, which is basically a parallel work share construct. Okay, so both are fine. It kind of depends on the on how would you write it depending on the situation. Okay, depending on how the code needs to be. Fine. So that is about the parallel combination construct. Now the other work construct that we have to kind of draw your attention to is known as the sections. So this is the sections work construct. Okay, now sections is a very it's kind of a useful and very easy to recognize and apply construct. Okay, because sections kind of what it does is it is going to this particular work construct is going to assign different pieces of work or different tasks to different threads. Okay, and the main caveat here is that each thread or only one thread will execute one section, right? That means, I don't know if this is clear, that means one particular section is only visited by one of the threads. So that means if you have, let's say, 3 threads and then 3 sections, then each thread will visit only one of the sections. Okay, so for example, let's say you have section 1, this is basically visited by or executed by thread 0, and then section 2 will be executed by T1, and section 3 will be executed by T3. Okay, something T2. Okay, something like this. Okay, so that is where the different tasks come into play. So that means, let's say if you have different sections, each of these sections represents a different task, then the threads will kind of do different tasks parallelly. So okay, so this kind of should ring a bell in terms of the task parallelism and data parallelism that we have studied. So this is kind of falls into the category of task parallelism. So it is, in many contexts, it's very easy to identify task parallelism in real world. See, for example, let's say take the example of the teaching assistants grading your assignments. Each of them will get to kind of do a different task. Okay, that means one teaching assistant will grade the first question, the other one will grade the second question, and so on. So the tasks are different, and each of them will grade their own particular question. Okay, so that means so we need to be only kind of identify how this kind of task parallelism can be used using sections. Okay, now of course this can be used when you have these tasks are independent. Okay, when the tasks are independent, then such a task parallelism can be used using sections. For example, let's say you have 2 vectors or 2 arrays for which, let's say you have an array A of n and another array B of n, and in the first task you need to calculate what is their sum. Okay, essentially calculate the sum of the arrays and then populate them into C of n. In the second task you need to calculate their let's say product. Okay, product of each of the entries. That means you need to calculate the product of A and B and then store them, each of their products, the array products, into D of n. Certainly the first task is very independent from the second one because it doesn't depend on C, and both of them only depend on the A and B, which could be kind of considered as shared variables. Okay, so in fact C and D can also be considered as shared variables, and as long as we make sure that only one thread accesses them at one time, right? Only one thread accessing them at any given time, right? As long as that is met, I think this can be also shared. Okay, that means how do you now write them? For example, so I would say you basically have hash pragma OMP parallel, right? Now again I'm writing a parallel work construct. Okay, so I'm writing the parallel construct. So then we have, let's say, the shared variables are A, B, C, comma D, and then we would have some do loop for loop for doing the iterations, or that in loop index variable I would like to call it as I, and that I'm making it as private. Okay, so we have the hash pragma OMP parallel, and then we have the hash pragma OMP sections. Okay, and then we would have an extra tag here. The extra tag is whatever we have already learned, which is the no wait clause. That means one particular thread need not wait for the previous thread to finish. Okay, so the sections need not wait for the other one to finish. So that means we have no wait clause here, and then we would open up and then write the, so here when you write, this should be sections. Okay, so this is sections, and then you have you would list down each of the sections here as hash pragma OMP section. Okay, so this is one section. This is basically executed by one of the threads. Then you have another section that is again hash pragma OMP section 2. So this is your section, and then this will be executed by another thread. Then you close the sections, and then you have the closing one. Okay, so that's how you do it. So each of them would be executed. For example, this will be maybe executed by T0, and this may be executed by T1, and so on, as long as you have so many sections. Okay, now the same thing of course can be written using Fortran. I would take the example of the Fortran also to complete the picture. So it's basically exclamation dollar OMP parallel, we have shared A, B, C, D, and then we have private I. Okay, and exclamation dollar OMP sections. Okay, that's what I had before, OMP sections, no wait. So in Fortran, no wait can be added towards the end, right? Because that is how it is supposed to be. Then in the sections, so this is one section. Yeah, so basically we have you start the OpenMP sections, and then you have each of the sections. So you have exclamation dollar OMP section. In the first section, we would, let's say, calculate the sum of the values. So do I equal to 1 to n in terms of 1, C of I equals A of I plus B of I. Okay, and then you would have and do exclamation dollar OMP and section, right? That's what we have. And the other section is completely independent, that is OMP. The next section is do I equals 1 to n. Now D of I equals A of I star B of I. Okay, that's basically the product of the array elements, and then stored into exclamation dollar OMP and section, right? Okay, and then we have, of course, we need to close exclamation dollar OMP and sections, and then here you would have a clause no wait, and then you would also end the parallel block, that is OMP and parallel. Okay, so this is the work share construct, and this is the parallel construct, right? Now of course you can also combine the work share and the parallel construct and write parallel hash pragma OMP parallel sections as well, just like you would write for do. You can also write in a combined way hash pragma OMP parallel sections, and then you have the clauses here. You know, you can have the list of shared variables, list of private variables, and any other clauses that you want. So again, this is basically a combined parallel work share construct. Okay, the same thing can be done in Fortran also. Fine. So that means this particular directive pair will allow to assign each thread a completely different task. Okay, and each section of the code is now executed once and only one by each of the threads, by a thread in the team. Okay, now of course there can be several instances in terms of, now what if the, you know, the number of threads is let's say is smaller or greater than the number of sections. Okay, let's say if the number of threads is greater than the number of sections, then of course some threads will be just will have no work. Okay, so essentially some threads will be idle if the number of sections is less than number of threads. Okay, now what if the number of sections is greater than number of threads? So those threads, the existing number of threads, all the number of threads will start executing the sections, and as soon as one of the thread finishes, then they will take up the following sections. Okay, so that is how it will be. Now that means, let's say if you have 5 sections and 4 threads, Okay, so that means what will happen is that first these the 3 threads, the 4 threads will execute the 4 sections. As soon as one of the threads from the team of 4 threads, okay, finishes, then that particular thread, that particular 4th thread, okay, I mean this 4th thread is the one that finishes, okay, first. So that 4th thread will take up the 5th section. Okay, that means while that 4th thread is working on the 5th section, if the other 3 threads have also finished, so those 3 threads will be waiting, right? That means when you have 5 sections and 4 threads, the 3 threads will be idle, waiting for the 4th thread to finish the 5th section. Okay, I think that's kind of nice and rhyming, so I would write it down. So basically we have 5 sections and 4 threads, then 3 threads will be waiting for the 4th thread to finish the 5th section. Okay, all right. So that kind of makes it clear on how threads will kind of work with the sections. Okay, so that kind of finishes the work share construct. There is one more there is one more work share construct which I am not going to do. It's actually called just work share. Okay, in OMP work share, which is actually only available for Fortran. So those who are into Fortran can kind of check this out. Those in C need not worry about that. So I'm not going to discuss about that in the lecture. Okay, all right. So then let us take a quick look at the some of the OpenMP runtime library API, the application programming interface that is provided by OpenMP. So how can we use and what these actually consist of? Okay, so basically OpenMP now provides OpenMP provides a runtime library API which consists of intrinsic functions. Okay, it consists of intrinsic functions. Okay, which actually serve as, all these functions will serve as control and query tools. Okay, for the query tools to the programmer so that these can be directly used inside the user programs. Okay, so that interface is provided, and all these intrinsic functions provided by OpenMP are available in OMP.h that we have already loaded in our C programs, or they are available in OMP_lib, which we are including by the with the use command in Fortran. Okay, so essentially let us look at these environment routines. So the first one is basically these intrinsic functions. So one category is basically your execution environment routines. Okay, so what are all the functions? Functions or routines. Okay, so we have already used some of them right by now, but anyway nonetheless kind of repeat all of them so that it will be complete. So the first one is basically your OMP set num threads. Okay, so I can write like this. So basically OMP set num threads, and then it will take an argument of number of threads. It basically takes a variable which is basically the number of threads that we can set. Okay, so OMP set num threads can be used inside the program. So inside a program, but it needs to be used, or it should be used outside a parallel block, right? Because you would not set the number of threads while you are inside a parallel block. So it should be used outside a parallel block or a region. Okay, and using which you can actually set how many number of threads should be used in the subsequent calls to the parallel blocks. Okay. So unless you change it, it's going to use these many number of threads. Now, of course, we also know that there are some environment variables that are available in that are provided by OpenMP, which also provides some kind of control. So the corresponding environment variable is basically OMP num threads. Okay, so you can basically also use a statement export OMP num threads equals, let's say 8 or something in your shell or console, so that all the programs will basically run with 8 number of threads. Now what will happen if you have that you have set this as well as you have set this in the program, then the precedence will be taken over by the call to this function. Okay, because this is set in the shell command, so the precedence is always for the intrinsic functions get the precedence. Okay, and whatever you write here in the shell will be overwritten by OMP set num threads. That is always the case. That is kind of a rule of thumb, or basically we can say that is the standard provided by OpenMP, or standard followed by OpenMP. Fine. Okay, so so you can kind of work with either ways. All right, the other one is very similar to OpenMP set num threads. This is basically the OMP get num threads. Okay, so this basically will return the number of threads that are available in a parallel block. Okay, so it's going to return the number of threads in a particular team. Okay, so that is what is OpenMP get num threads. Now OpenMP get num threads, unlike OpenMP set num threads, can be used anywhere. Okay, it can be used either inside the parallel blocks, or it can be used outside the parallel blocks. If it is used inside the parallel blocks, it is going to return the number of threads. If it is used outside, then it is going to return 0, which says that which basically will return 1, which says that there is only one thread, that is the master thread, that is available. Okay, if it is outside the parallel block. Also, if it is called from a serial region, let's say inside a parallel region, let's say if it is called inside a single region or OMP master region, then it's going to return only 1, because that is the only one thread is kind of participating at that particular line in the code. Okay, all right, so the other one is basically OMP get thread num. Get number of threads, get thread num. Okay, oh, I think we didn't look at we never looked at OpenMP set num threads. I guess we only gave num threads as an argument for parallel for, that's all. Okay, so now you can use. I think we have been only using get num threads and then get thread num, right? So get thread num, you also know this basically returns the rank of a particular thread on which it is run. Okay, or this is also going to return an identification number for a current thread. Okay, so it's basically going to return an identification number, right? How do you identify a particular thread for a thread, so that you can identify them. Now again, if you run it inside, if you run it in a serial, then it's going to just return 0, saying that the master thread has a 0 rank. And if it is called from let's say in a parallel block, it's going to return its own particular identification number, as such as 1, 2, 3, and so on. Okay, Now if you run it inside a serialized parallel block, okay, so that means then it's going to again return 0 because that is the only one that is available. All right. Okay, then you have another query function that is known as OMP in parallel. Okay, again this is going to return either 0 or 1 in C, or it's going to return true or false in Fortran. Okay, so what this basically tells you is that is OMP running in parallel or not. Okay, so if you are inside a parallel block, then it's going to return 1, otherwise it's going to return 0. So sometimes you may be required to check this before you implement something. Okay, so for that reason this acts as a query tool where you can check whether a particular block of code which you are executing is actually inside, is it in parallel or not. Okay, so that is what this is used for. Okay, then we have a few more intrinsic functions. That is basically the next one is OMP set dynamic. Now this needs to be called let's say with a logical operator. It says in Fortran you would call it with either true or false, and then in C you would just call it as OMP set dynamic, and you would pass either 0 or 1. Okay, that is in C. Now what this basically does is it will instruct OpenMP to set the dynamic threads. Okay, essentially it will either enable or disable the adjustment of the number of threads that are available for execution in parallel. Okay, so basically this is used for adjusting the number of threads available. Okay, it will be adjusting the number of threads available for execution in a parallel block. Okay, that means let us say so once you set this thing, so that means if you set the dynamic threads to be on, then what happens is that then OpenMP is free to choose the optimum number of threads, okay, that are required for any particular parallel for or do. Okay, so that is what OpenMP does on its own. That basically does it automatically. It will decide how many threads are optimum, so that it can basically use the shared memory resources of the computer in a more optimum way. Okay, so but then we may wonder, now what about if I set dynamic threads on, and if I also set OMP set num threads, right? We have just learned about this. Or what if I just set the environment variable outside? Okay, so in both cases, either you set the number of threads or you basically set the environment variable OMP num threads. In these cases, whatever you set now would be treated as the maximum number of threads that OMP can use. Okay, so it will not cross, although it automatically will use the number of threads. That maximum is kind of restricted by the number you would set here. Now if you do not set any of these things, then OpenMP is kind of free to choose optimum number of threads that are required for a particular for loop or a do loop. Okay, so that is what the meaning or the behavior would be. All right, so the next one is basically another query tool that's called OMP get dynamic. So this is the counterpart of OpenMP set dynamic. So once you call this one, so it basically returns whether the dynamic threading is enabled or disabled. Okay, by either true or false, or using 0 and 1 in C. Okay, all right, so the next one is already we have kind of quickly discussed in one of the last question and answer sessions. That was OMP set nested. Okay, so this will actually basically set parallel nesting, okay, or nested loops to on or off, okay, to enable or disable. Okay, that means if you set OMP set nested to 1, then it is going to allow, or you say true in Fortran, or you say 0 or dot false. Okay, now this is going to allow nesting of the loops, okay, which we have already seen. So for example, you can also set this, instead of setting inside the program, you can also set it using the export, using the environment variable. That is basically, you can write export OMP nested. Okay, you can set it to 1 and export in the bash shell. Okay, that's basically the environment variable. Now what if you do this, then what happens is that if you already have a couple of threads that are already in the parallel region, then another level of threads can be forked from each of these threads. Okay, so that means, as we saw, as was asked, as you know, discussed by Venu, or question raised by Venu in the last class. So let's say if you already have a hash pragma OMP parallel, let's say I have num threads, okay, num threads 2. Okay, so before this I have already set OMP set nested to 1, so that this behavior is supported. Then I have already 2 threads that are created, that is basically your T0 and T1, and I have some for loops or whatever. And then down the lane I have here hash pragma OMP. I have another parallel num threads, right, 2. So I have kind of asked for another 2 more threads. Then you have some code here, then you would close this one and you would close this one. Okay, then what happens is that earlier, so to begin with, we have, once it encounters this parallel region, you have T0 and T1 being created by the T0 thread. Okay, then once you do this thing, once it comes here, then the T0 here would again create, you know, more T0 T1, and this would again create T0 T1, and so on. Okay, that means it would basically end up with 4 threads, and the numbering, I suppose, would be 0, 1 and 0, 1. So that is what is basically a nested functions, right, or nested loops or whatever, right? So that behavior is only is kind of can be emulated using this particular by enabling this particular function, okay, or by enabling this particular variable. Now this may or may not be useful in all the contexts, so we will see if we have to make use of this, but we have to be extremely careful now in terms of how the data is you know, shared between the threads and so on, because this may get very complicated if you go to even just to 2 to 3 levels. Okay, and many a times it may not be actually required to do nesting unless it is absolutely you know, felt essential. All right. Okay, so the next the one more runtime library intrinsic function that we would like to look at is look at the basically the query for the status of the nesting, right? Query the status of nested loops. That means you would just use OpenMP get nested. Okay, so that's going to kind of return again a 0 or 1 or true or false, and then tell you what is the status of the nested parallel mechanism. So to know the status of the nested parallel mechanism, fine, that's basically just a query tool. Okay, so that kind of finishes the environment intrinsic functions, and I would kind of we will kind of wrap up the lecture with a couple of more intrinsic functions or runtime library functions provided by OpenMP, which are very much required. These are known as the timing routines. Okay, that means how do we time our programs? Timing routines. Okay, how do we measure how much time you know, each of the let's say some block of code in the OpenMP code is taking or something like that. So basically this will the timing routines will actually measure the absolute wall clock time values. So to measure the absolute wall clock times. Okay, we use these routines, and also to serve as evaluation tools for the parallel program. Okay, that means how good is our parallel program, how much time it is consuming compared to the serial version. Okay, so in order to know that, we need to know what is the time consumed by a particular subroutine or a particular program. Okay, so there are a couple of functions. One of them is much more useful, that is basically your OMP get W time. Okay, this is get W time. So this basically, this function call will return a double precision value. Okay, so you would basically require a double precision variable to store it in Fortran, or you would need a double in C, okay, to store it. So it returns a double precision value for the absolute wall clock time. Okay, so now, okay, that means that it's going to just return a particular absolute wall clock time value at that particular instant. That means at that particular instant where the code encounters this statement. Okay, that means we get one time. Let's call it as let's say T1. If you make a call to this, you can say OMP get W time. Okay, now T1 is again a double value, so that is your is kind of a start time or something like that. So what we need to do is, in order to time our programs, we need to call this particular function 2 times. So that means you have this function, and then you would have a piece of code here, right, which you want it to be timed, and then you would again call it later with T2 equals OMP get W time, right? Now that means you're calling it 2 times, and the second time it's going to return another value, and if you subtract one from the other, so T2 minus T1 is going to basically give you the time that is elapsed, right, between these two, so between the function calls, right, or essentially it will approximately give you what is the time consumed by this particular piece of code. By the enclosed piece of code. Okay, so that means that is how we can kind of time our programs. But then one question comes here: is this time the sum of all the threads time, or is it actually per thread? This is actually a per thread time. Okay, and this time should not be or this time may not be relevant between threads. Okay, so that means that you have to always make sure that these times that you measure are private to each of the threads. Okay, so if you were to know what is the total time consumed by all the threads, then you have to kind of sum them up. So this is whatever the time you get would be the per thread time. Now that also says that the absolute wall clock times on or between the threads may not be in synchronization. Okay, so may not be in sync. So that means you would not try to compare T1 coming from one particular thread to T2 coming from another particular thread. Okay, you would not do that, because the wall clock times absolute wall clock times may not be actually consistent. Okay, so they are not globally consistent between the threads, so as a result you will not compare that. Okay, so they are not globally consistent. Okay, now that is about the timing subroutine or function. The another less used one is basically to query about what is the the precision of this particular timing routine. So that function you can call using OMP get the W tick. Okay, so basically get W tick is going to tell you the precision in seconds that that can be measured by a particular thread. Okay, fine. So that means basically, so this is nothing but this is the number of seconds between one or between successive ticks of the clock. Okay, so that basically will give you what is the precision. So if you want to know how many ticks have happened or something, then you have to divide whatever is the time with these seconds to get number of ticks. Okay, number of clock ticks or something like that. Fine. So you can you probably may not use this much. Rather, you would use the first one, that is OpenMP get W time, more often, because whenever you want to kind of time your subroutines. Of course, whatever we discussed till now is kind of finishes all the OpenMP directives, okay, plus some of the runtime library routines, which are kind of felt that are sufficient to get started with OpenMP programming, either for general purpose or for numerical methods. Okay. Now, of course, this is not certainly a very comprehensive list of runtime libraries. You can find all of them on the OpenMP standard on the website, but I feel these are sufficient to get started with our programming for numerical methods in the coming lectures. Okay. So so that kind of finishes the OpenMP programming directives and discussion on the runtime library functions and things like that. Okay, so I'm going to stop here. We will catch up from here in the next lecture. Okay, thank you.